Hi everyone, my name is Albert Yang. I am a student taking ECE 4470, which is Systems 1, and I'm taking it with Dr. Finn Lin. And this video is just going to be an overview of the first major concepts you would learn in his class for control systems. And that would be the signal flow graph and the Mason's gain formula. So a signal flow graph is basically just a simplified version of a block diagram. So you take in linear systems and signals, then you'd most likely be familiar or introduced to block diagrams. And then usually they would have you try to find the transfer function. So an easier way to find the transfer function without doing a lot more math is to use Mason's gain formula, which requires a signal flow graph that is the simplified form of the block diagrams. So here I have an example on the left of a signal flow graph, and the little circles that you see, like these ones, those are called nodes, and they represent the different variables you would have in the corresponding block diagram. And the ones you see on the ends, like the Y1 and the Y2, or the Y5, this one is the input node, which means it doesn't have any branches coming into it, and it's only having outputs going to other branches. While the Y5 is the output node, so there's only things coming in, and it's not sending anything out. Then for a path is just any line that connects two different nodes that are next to each other. So we did Y1 to Y2, then that would be a path. And then a forward path is a specific type of path that goes from the input node to the output node without repeating any of the nodes. So the most simple one is from Y1 to Y5 straight through, and with the Y1 to Y2 to Y3 to Y4 and then Y5. And then the forward path gain would just be the product of all the different branch gains that you go through when you go through the forward path. So you can see that there's G1, G2, and G3. These are the three path gains between the Y2, Y3, Y3, Y4, and Y4, Y5. So when you go through all of these in one forward path, then you would multiply these three together along with the ones. But since these are ones, you can ignore them. So it'd be the path forward path gain for this first forward path would just be G1, G2, G3. And then there can be multiple forward paths for the signal flow graphs. So another one would be from Y1 to Y2, but then instead of going from Y2 to Y3, you go from Y2 to Y4 with the top right path, then to Y5. And then that one would have a forward path gain of G4, G3. And then the next part that's relevant to Mason's gain would be the loops. So a loop is when you start and end at the same node without repeating nodes. And this, unlike the forward path, does not need to start at an input node. So one example would be Y2 to Y3, and it just goes back to Y2. Then the loop gain would be G1 times negative H1. So it's just against the product of the gains. And then another one you can find would be from Y4 to Y5. This would be G3 times negative H2. And then there's also another one here, the larger one would be G1, G2, G3 times negative H3. And then this is relevant for Mason's gain formula that I'm going to go over, where you find the gain or the transfer function of the signal flow graph, where M is your gain, like overall gain, also the transfer function, and that's equal to the Y out over Y in. Those are the output node and input node respectively. And it's basically going to be a sum of the MK times delta K, where MK is the path that you have. So if you have 3 paths, then you would label them as M1, 2, and M3, where N is the number of paths that you have. And then for the delta K, that's going to be the determinant. But for when you remove that specific path, and then the determinant, the overall determinant is just the delta, and that is going to be, it's always going to be 1, then minus the sum of all the individual loop gains. So you need to be able to find all the loops and find those gains, and then add them together. Then you have to subtract that from 1. And then there's also going to be plus the sum of the gain products of 2 non-touching loops. So in our example, that would be, say, these two, they're not touching. Then you need to multiply the gains together. And then if you have more than one pair of these, you would add them together and then add it to the 1. And then it goes on, but usually we would only get to the two non-touching loops, and then we don't get into the set of 3. And then N is just how many paths you have. So you would actually repeat this for every path that you have. Every 4 paths. And then so let's do an example problem just to get familiar with this. And then what I like to do is find the overall determinant for these types of problems, because they're going to stay the same for those specific problems. And so let's find all the forward paths and all the loops, and then we can go from find the determinant. So the first forward path is going to be from Y1 to Y7 all the way through. And then I'm going to write that as M1. And then we're going to just write the sum of the gains. So it'd be 1 times G1 times G2 times G3, G4, and G5. Then there is a second loop that would be from here through the top part and then all the way through. That I would call M2. And then the 1 and 2, those are the K's that you would have in the Mason's gain formula. So this one would be G6 times G3 times G4 times G5. Then you can also rearrange this to be G6 at the end. And then for these, you also want to find the loops that are there, and there should be 4. So let's go with the first one. We can go from, say, Y2 to and back. So that'd be rather no, it'd be, yes, that could work. Y2 all the way through to Y7 and then back. That would be 1. And then this would be, let's see, this would be G1. We're going to do the loop gains. G1, G2, G3, G4, G5. And it's also going to go through negative H3. So we put H3 and then it's negative. And then we also have 2 small ones. That would be like this one. That would just be G2 times negative H1. And then we have another one here. That would be G5 times H2. And then H2 is negative, so we've added a negative sign in front. And there should be another one from, let's see. Yes, there's another one from, let's see, here. We can also go here and through. And that's a different loop. So that would be G6, G3, G4, G5, and H3, and it'd be negative. Right, so then once we make sure that we found all the loops, then we can just write the for loops. And that means we're going to need to do the summation. I think, no, we just need the for loops. And then the summation is actually just going to be 2 because we have 2 forward paths. Then we also need to find if there are any pairs of non-touching loops. And the easiest way to do that, especially when you start doing like more complicated ones, is to label what nodes these ones go through. And then if you have shared the nodes, then they're not non-touching. So for the G2 to H1, that would go through nodes through Y3 and Y4. Then the G1 through all the way to G5 and H3, that would be Y2, Y3, Y4, Y5, Y6, and Y7. Then the G5 and H to H2 is Y6, Y7. And then G6 to G3, that would be Y2, Y4 to Y5 to Y6 and Y7. Then I think you can actually see it. This one is easier. You can just see that the 2 blue loops are non-touching, but the most efficient way is to compare all these with each other. So you would go with, say, let's start at the top, Y3 and Y4. Then if you see Y3 or Y4 in any of the other ones, then those would not be paired. So for, say, these two, there's Y3 and Y4, so it's not going to be a pair. But this one, these two, they don't share any of the same nodes. So one of the non-touching pair would be the G2H1 and G5H2. And then let's check with the the third one, so that's this one. This one also has y4, so it's not going to be a non-touching pair. Then you would go to, you would start with the second one, and then you compare to anything below that. This one has y6 and y7, which matches these two, so there are no non-touching pairs. Then if we do this one, it's y6 and y7. It doesn't match with, or it matches with these two, so they're also not non-touching. So in this case, we would only have one pair of non-touching loops. Then when we do the determinant, let's go, that would be maybe 1 minus, then let's go back to our formula. It says 1 minus the sum of individual loop gains. So that would be 1 minus, then negative, so we have 4 loops, that would be negative G2 H1 minus G1, G2, G3, G4, G5, H3, then minus G5, H2, minus G6, G3, G4, G5, H3, and then let's add another page, and then plus, then you need to do plus the gain product, the sum of the gain products of the two non-touching loops. So that would be plus negative G2 H1 times negative G5 H2. Then if we simplify this, we would have the determinant is equal to 1, and then notice that all of these individual loops have a negative sign in front. So when we do a negative, like minus all of these, it's just plus. So V1 plus G2 H1, G2 H1 plus G1 G2 G3 G4 G5 H3 plus G5 H2 plus G6 G3 G4 G5 H3. And since these two are both negative, when they're multiplied together, the negatives cancel. It would just be plus G2 G5 H1 H2. And then this should be our determinant for all the problem, or all the parts to come. And then when we wanted to, let's check part A, they asked for y7 over y1 when y8 is 0. So let's do A. We need now the reason why they have this annotation here with the y8 is equal to 0 is because we actually have two possible input nodes, the y8 and the y1, and you can't have both at the same time, or they don't want you to. So that's why they tell you that y8 is 0 for the first one. So then y1 would be our input, and we would pretend that y8 is not 0. So let's do the, we would need to find the forward paths for y1 to y7. And then we basically did that when we did the overall, when we found the overall determinant, right? So that would be G3, G4, G5, G6. as well as G1, G2, G3, G4, G5, because it's just going all the way through. So when we do the M1, that would be G1, G2, G3, G4, G5, and then M2 would be G3, G4, G5, G6. Then now we have to find the determinant K, or the delta K. So those would be deltas 1 and 2 to match with the paths 1 and 2. Then, well, the first one is actually pretty easy. But what we're going to do is we're going to check. So we have 4 loops, and we need to see how many are left after we remove that specific forward path. So if we go with M1, if we remove that whole thing and all the nodes included in that, then all of these nodes are gone. Then you can't make any loops with that. So the loops would be 0, which means that it would just be 1 minus 0. It's just still 1. So that's why our first determinant is going to be 1. And then if you do G3, G4, G5, G6, that's from here. So this will basically take out all of the loops as well, because let's see, then you can also look at the these nodes again when you're doing this, because if we go from G6 to G3, then that means Y2 and Y4 are out. So this loop is out, then this loop is out, then Y6 is also out. Yeah, Y6 is here actually. Y6 is also out, and then you know that if there's also a Y6 for this part, then here is also out. So none of the loops are going to work for the second one as well. So it's also equal to 1. Then when you do M, this would actually be M equals, then they want you to do the sum, right? And it's going to be mk times the delta k. So that would be m1 times delta 1. And because of the summation, it would be plus m2 times delta 2. And then you repeat this n times for the nth k. So since we only have 2, then we only have 2 for loops, then we only have the m1 times delta 1 plus m2 times delta 2. Then we're going to divide our sum with the overall determinant that we found earlier. So then you could do m, or you could do the y7 or y1, y8 equals 0 is equal to then m1 delta 1 plus m2 delta 2 over the determinant. And we're going to add another page. Then we can substitute, and that would just be G1, G2, G3, G4, G5 times 1 is just the same, then plus G3, G4, G5, G6. Then divide by the determinant. And the determinant is usually pretty long, so it's usually acceptable to just leave it as this, as long as you highlight that you've already found the determinant earlier. Then, yep, that's good. So now we're going to do part B, and that one asks for, let's see, y7, y8 when y1 is 0. So now they're going to ask us to go from here. You want these two instead, and then we ignore this part here. So let's try that. Then let's do y7, y8. And we're gonna check how many forward paths there are from y8 to y7. Then we can see that there is one that goes all the way, and then there's no other loop or no other forward path that we can do to get to y7. So there's actually only one this time. So it would be one forward path, and the m1 is equal to, then we check, this is g4 times g5, and then times 1. So m1 is g4, g5. And then now when we do the determinant, the first determinant, or delta 1, that's going to equal 1 minus. And then we're going to see what happens if we remove g4, g5. So if we remove g4, g5, that means y5, y6, and y7 shouldn't be there. So then we would check how many loops are still available. That would be, looks like that would be just this one. y3, y4, and that one's okay, because we're removing y5, y6, and y7. So then we look at the next one. This one has y5, y6, and y7, so this one we wouldn't be able to use. And then the same for the last three. So negative g2h1 is the only one that we have. So it'd be like this. Yes. Then if you simplify, this just becomes 1 plus g2h1. So when you find the transfer function here, it would actually be m1 times delta 1, which is g4, g5, and times your delta 1, which is 1 plus g2h1, divided by your determinant. And it's the same since we're using the same signal flow graph, right? Then we're going to go on to part C. And this asks for y7 over y4 when y8 is 0. And then this is interesting because it goes from y4, they ask from y4 to y7, but they don't want y8. But you wouldn't really want to do this from like just like what we did before, because this one is not an input. So instead of doing that, we would do something like y7 over y1 divided by y4 over y1. And what happens is that the y1 would cancel, and then you would end up with y7 over y4. And this is helpful when you've already found the y7 over y1 and the y4 over y1. Now we already have y7 over y1 because that was part A. And then we need to find the y4 over y1. So here we have and then I like to write out. So we have this. Then we define y4, y1, and then y is 0. So let's go to y4 to y1 and see what we have. So y4, or rather y1 to y4, that's here, with these two. And the first forward path is from y1 to y2, y3 to y4. And then the second forward path would be using the top part here. And there aren't any other ones. So then we only have two forward paths. So we would say M1 is equal to, let's check. M1 is G1, G2, and then M2 is just going to be G6. Then when we do the deltas for the determinants for these particular ones, we would remove the corresponding forward path and see what loops are left. So for the first one, it would be the G1, G2. So G1, G2 means we would do, we need to check for Y2, Y3, and Y4. So this is, and we'll check each of these again. So if it has Y2, Y3, or Y4, then that loop is not going to work. So that's the first one's out because it's Y3 and Y4. And this one is also out because it has all three. Then this one, the next one here is actually okay. It works because it's Y6 to Y7. And then the last one is also out because of the Y2 and Y4. So that would be, so for delta 1, that would just be negative G5H2. Which equals 1 plus G5H2. Then the second determinant is going to be 1 minus, and we're going to look for G6. And G6 will have Y2 and Y4 nodes that we don't want. So let's check again. So the first one has Y4, which shares this one here, Y4. So that one's out. And the second and fourth ones also both have Y4. So it's actually the same. This is the only one that works, which is negative G5H2. And that gives us 1 plus G5H2. So when we do the transfer function of Y4 over Y1, that gives us that'll give us, let's do M1, that's G1, G2, times delta 1, which is 1 plus G5H2, then plus then G6 times 1 plus G5H2 divided by our determinant. And we can simplify this further by factoring with the 1 plus G5H2. And that would give us G1, G2 plus G6 times 1 plus G5H2 divided by the determinant. But they want us to find y7 over y4. So we need y7 over y1 divided by what we just found here. So let's go back to find, or we have y7 over y1 would be G1, G2, G3, G4, G5 plus G3, G4, G5, G6 divided by the determinant, and that's going to be the y7 over y1, and this is going to be divided by our G1, G2 plus G6 times 1 plus G5H2 divided by the determinant. So this would actually be, if you do division by a fraction, then you can flip it. So this is the same as times the determinant over G1, G2 plus G6, 1 plus G5H2. And you can move this up. Then that means the determinants actually cancel. So our y7, y4 would actually be, let's see if I can, it would just be G2, G3, G4, G5, G3, G4, G5, G6. And when you're given these homework problems, it's gonna get kind of long and tedious just because you have to keep writing a lot of these. So make sure you start early, because for this particular class with Dr. Lin, the homework solutions are actually all given, and you just need to show your work that and that you're able to get to those solutions. So you wouldn't actually need to worry about having to do it, whereas there's since they're all given, then you just need to be able to get to that, and it just takes some more time. So let's see, it's G1, G2 plus G6, 1 plus G5, H2. And this is our final answer for C. And then for part D, they actually want the same, but this time they want y1 is 0, which means we're going to be using, which means that we're going to ignore this. We're actually going to be using this one here. And so let's write that down first. That would be maybe y7 over y4. And that would basically, we would need y7, y8. Since y1 is 0, we're using y8, so that's why we have y7, y8, and then just be y4, y8. And then we would need, I think, let's check y7, y8. I think we have that. We have that in part B. with y1 equals to 0. Yes, so we have, and then we need to find y4, y8. So right, then let's go back to here. And then this one is a little trickier, where we have y8 and this is y4, but you don't want to go from here to here because the paths can only go in the direction of the arrows. So if you go down, you can't go to the left because the arrow is pointing to the right. So you need to find another way across. And that would be from here then to here, then all the way back to here, and then back. That would be one path. And then we don't see any other paths to get there because if you go with just small loop, then you're going back to y6. It's repeated, and that doesn't work out. And then if you try going through here, like this, then you'd be repeating the y3. So we actually only have one forward path here for the last problem. For the y4, y8, this would be 1. Then m1 is equal to, then it's going to be a long one. So let's see. I'm going to write it here instead. So it would be G4, G5, then H3 is negative, then G1, G2, G3, or G1, G2, and then it stops at y4. So it's just going to be G2. Or rather, there's actually 2. Oh, sorry about that. There's 2 because we also have this top one here. And that would be negative G4, G5, H3, G6. Alright, so there's 2. So there's yes, these are the 2 that we need. Let's see if I can copy those over. So we don't need to. Okay, it doesn't work, so I'm just gonna have to write it out again. So the G4, G5, H3, G6. And then M2 is equal to the G4, G5, H3, G1, G2. Then let's check what happens if we remove these forward paths and how many loops we'll have remaining. So if you look at this, this would be y5, 6, 7 for the first one. 5, 6, 7, 2, 3, 4. We know that y4 is included, so this one's not going to work. And then this one has y4, 5, 6, and 7. This has 7, so they all have 7. So that means there are no loops for the first one, which means the delta 1 is 1. Then for M2, delta 2 would be, let's see. Then y3 here would actually be, wouldn't be included, but then you still have y7. So we know that these three are out. And then it still contains y4 here, which means this one's also out. So it's also going to be a 1 for this one. Then we would have y4, y8. And that would just be G4, G5, H3, G6 plus, or yeah, G plus, but then the other one is also negative. So negative, and G4, G5, H3, G1, G2. G4, G5, G3, G6. Then you can also rearrange these, but okay. And then you can also simplify it by factoring out the common ones. That would be negative G4, G5, H3, then G6 plus G1, G2. Because these are these three. So this gives us the G4, G5, H3 times G6 plus G1, G2 over the delta. And that's the y4 over y8. Then we have y7 over y8. And that would be, see, here. Okay, right. This is y7, y8, or y1 equals 0. Then now we take this and we divide it by the y4 over y8. That would be dividing by this one here. And now let's simplify to, we know that this would cancel. And we would have negative G4, G5, divided by G4, G5, H3 times G6 plus G1, G2. And then that is the final answer for D. And then they asked us one last thing. They asked comment why the results for parts C and D are not the same. So we know that they're both y7 over y4, but then they're different because for C we have G1, G2 plus G6 times 1 plus G5, H2. And that's different from the, wait, never mind. That's actually these two. So the, let's see. Y7, Y4, Y7, Y4. Oh, that's this one here. And it's going to be that versus these two. So yes, they are different. And the reason they're different is because we have different inputs from here versus the y8 is 0 versus the y1 is 0. And then I hope this was helpful and good luck when you're taking this course. Thank you.